Alright, welcome back to the second part of the lecture about gear efficiency. We will continue where we ended in the previous part with a mathematical expression called efficiency. And as you may remember, this expression tells us what are influencing the efficiency. The friction coefficient is of course an important parameter. The bigger the friction coefficient, the bigger this term will be, the lower the efficiency will be. The helix angle, the bigger the helix angle, the smaller the cosine will be, the bigger this term will be. The pressure angle or angle of action alpha is more or less a constant. It doesn't vary very often, but the pitch radii may vary. That's the size of the gear. So the bigger the number is here, the smaller this number is, and this number will be smaller. So the bigger the wheels are, the more efficient it will be. Remember now that efficiency is varying over the whole engagement period, and if you want to have some more average number, you can first of all you can compute the efficiency at all points along the line of action, but you may also want to have more average total number, and you can do that by defining some average values of the different parameters, such as an average offset and average values of the of the coordinate where you study the most representative coordinate along the line of action and the friction coefficient. These two are required to determine a kind of average offset delta m. In literature, you can find that it's a reasonable approximation to take 1/4 of the complete length of the line of action from where engagement starts at A and ends at B, and in the middle between the first engagement and the pitch point, it's a reasonable average position or representative position for the PT. That means that the PT is the distance AB divided by 4, and it's possible to show that this is you can find that as a product of the contact ratio and the base pitch divided by 4. So putting that into the expressions, you get an average of the delta, that is this one, and you get an average efficiency expression that looks like this. And you can then express some of these parameters, the pitch and the pitch radii, can be expressed in gear parameters instead, and then you end up with an expression like this. So now let's see here. Again, low friction gives you high efficiency. That means that you should work on with the lubrication, the materials, surface finishing, surface treatments, etc. You can see that the low transverse contact ratio, a low contact ratio is good. That means that there should be as few gear teeth pairs in contact as possible all the time. If you have many gear teeth, this is a big number, this will be a small number that will give you a high efficiency. So many gear teeth is good. If you express this also in module, that means that you should have very small and many gear teeth. Well, infinitely number of gear teeth could be the best. That means that you have 2 rollers in contact, but that will give you other problems. But in general, small and many gear teeth are good. And again, a small helix angle is good. So that's the reason why racing cars use spur gears. You can hear that on the noise. yeah, so just to illustrate this now, two curves here. These two curves, the same friction coefficient, but different helix angle. And you can see here the general trend is that the more gear teeth, the higher the efficiency. It's almost 1 in this up here. But if you compare these two curves, this is the one with beta helix angle 0, and this is helix angle 30 degrees. And you can see that you can get pretty big improvement of the gear efficiency. Remember that even a fraction of a percent could be good. These two curves can also be compared to see the effect of the friction coefficient. So if you reduce the friction to half from 0.1 to 0.05, you actually half the losses also, as you may expect. You can see that this is the loss, the distance here, and if you half the friction, you half the loss. And again, you can see the efficiency is high, except down here where you have very few gear teeth. Then you can lose 2-3% in each engagement. Then in a gearbox, of course, you don't have only one gear engagement. There could be many in the same gearbox and same transmission. Okay, that was about the important parameters. Now a few words about how to measure efficiency. We normally do that by using something called power recirculation, and that means that you put two identical gears back to back. So you have the two wheels are connected and they are driving the two pinions. You apply a torque into this shaft by twisting this shaft relative to that one. That gives you a built-in torque in the gearboxes. So now you can drive this pinion, can drive this gear, which drives this gear, which drives this pinion, which drives this pinion. And so the power is, so if you apply a high torque here, the power is just circulating around here. If you don't have any losses at all, it will just be a power circulating here. It's kind of eternal machine. But we have losses, as you know, and the electric motor here is just there. It gives you the speed, of course, but it also gives you the compensate for the losses. So put it like this: the electric motor only needs to compensate for the losses, not more. So you may have 100 kilowatt circulating here, but the electric motor only needs to add 1 or 2 kilowatts. That's the beauty of this machine. You can run very high powers without using very high input power. This is just another picture of how the power flows are going here. This is a very typical type of rig, and maybe the most famous is the FZG test rig, which is invented in University of Munich in Germany. And here is the torque applied, and the dead weights are applying that torque continuously. You can read about that if you Google it. This is a rig, we actually have one FZG rig in Luleå University too, but we also made another type of power circulating test rig, and this is 2 gearboxes from a Saab. And so here you have the 2 identical gears, one here, and one here. And this is the loading clutch, and the electric motor is outside here, outside the box. And maybe the most important factor in this expression is the friction coefficient itself. As you can see from this, it varies. Maybe you can't see it from the expression, but you will know that it varies along the line of action, because we have different degrees of sliding in different positions. And now if we assume that we have elastohydrodynamic lubrication or mostly full fin lubrication, we can discuss that a little bit. First, I just want to say or show this that the engagement of two gear teeth is not a very static event. It's everything's varying. So as we know, the sliding varies. It starts with high sliding in the first engagement, and then it goes down to 0 in the pitch point, and then it goes up to much sliding again in the very end. And that means that also the slide to roll ratio varies from high to 0 to high again. The gear tooth load could look like this, that in the beginning you have two pairs of teeth carrying the load, but around the pitch point only one gear teeth pair is carrying the load. Then the load is doubled, and then a new pair is coming into contact, and you get reduction of the load again. The entrainment speed, the average speed of the surfaces, is also varying all over along the line of action, and so do also the effective radius, which is the you remember from elastohydrodynamic lubrication that you need a radius, kind of effective or equivalent radius of the cylinder in contact with a flat plane. And if you change the curvature of the gear teeth in the different positions, you will find that the effective radius is varying from first engagement to last engagement, something like that. And we have computed the friction coefficient along the line of action, taking into account the different degrees of sliding and load, and now assuming full fin lubrication, then it could look something like this. We use two different oils, one synthetic polyalpha-olefin, one mineral oil, which is a traditional oil. And you can see here that the friction is high. This C coordinate now is the PT coordinate, we called it PT in previous slides. So this is the first engagement, this is the last engagement. 0 means the pitch point. High sliding, high friction. The sliding goes down, and so do also the friction, until here when suddenly one pair of teeth are coming out to contact, and the load is carried only by the contact point now. So the friction goes up, but then it goes down again, since the degree of sliding is decreasing, and eventually it comes to more or less 0 in the pitch point, and then it goes up again. A new pair of teeth is coming in contact, then it drops rapidly, and due to the increase in sliding, it goes up. And the difference here between the red and the polyalpha-olefin curve here is due to different lubricant parameters. So this can illustrate that if you select lubricants with what we call the limiting shear strength properties, which are good and beneficial, such as for this synthetic oil, you can reduce the friction pretty much in contact. And this is not the viscosity doesn't really play a role here. It's more the limiting shear strength, which we discuss in the elastohydrodynamic lectures. We can measure this friction. Of course you can measure it in a gear test rig, but that's a more time-consuming test and also expensive test. And it should be simpler to use a ball on disc tribometer. In this case, you can control the conditions very much better also. So you have a ball driven by a separate motor, and the disc driven by another motor, and you can adjust the speeds of the ball and the disc to any slide to roll ratio. You can adjust the load, and you can adjust the entrainment speed, and you can use many different lubricants here. So this is a very versatile machine and very useful machine to learn about EHL friction. And then again, you get this mu-slit curve I showed you before in the part 1. So this is a typical result from the ball and disc machine. At no sliding, low sliding, the friction is more or less 0. and it increases rapidly when you start sliding, reaches a maximum since you reach some limiting shear stress, and then due to heating it goes down a little bit. It varies also a little bit with entrainment speed. Higher entrainment speed means more heating and there's also lower friction. Another typical curve we use is a Stribeck curve. Again, well, you recognize this from maybe not. This the Stribeck curve for EHL looks a little bit different from that from journal bearings, but up here at low entrainment speed you have mixed lubrication and high friction, but then it goes down with speed, and with increasing speed you get more heating and then also lower friction. The higher the sliding, the more heating, the lower the friction coefficient. Remember that this is the coefficient. We used to put these diagrams together to one 2D map, so you have the mu slip curve in this direction and the Stribeck curve in this direction. You can make these maps so you have a number of Stribeck curves in different slide to roll ratios. This is useful. Then you can learn about how the friction varies with these two important parameters. So this map could be made for one certain load. And here are some regimes identified. We're not going to talk too much about that, but this regime is the mixed lubrication regime. So at low speeds you have mixed lubrication here in this part of the system. So the friction increases here, and there's a, if you are used to maps, this could be like a ridge here, and here the maximum friction is following this line somewhere. So here it increases, but these lines are meaning decreasing friction actually. So the friction coefficient is probably smallest in this point, and of course along down here where you have rolling. This diagram or this 2D map can be used to follow the path of contact through the EHL. So as you remember, high sliding in the beginning of the engagement reduces over and reaches the pitch point and goes up again. And since also the entrainment speed varies, if you have two different gear wheels, which you normally have, you want to have gear ratio, it forms something like a V-shaped motion through the to the friction map. And that means also that you can determine the friction coefficient in any point along the path of contact. And if you can relate this mu to the position PT, you can actually define the efficiency in any single point of contact. And if you have that efficiency curve, you can easily find the average loss too, of course. We have made these friction maps study different effects, and one effect is of course viscosity, as viscosity is what we discussed before, is the trend to try to reduce the viscosity of the gearbox oil, since low viscosity will give you lower splash losses. And you may then also assume that low viscosity will give you lower losses in the gear contact. But unfortunately, even if we don't come into mixed lubrication or boundary lubrication, even in full film lubrication, the low viscosity maybe a little bit surprisingly give you higher friction in the EHL contact, because in the EHL contact you have other effects than viscosity effects. It's more, as I said before, shear strength effect, and this shear strength is actually a little bit higher for a low viscosity oil than for a high viscosity oil. So you can check this by choosing, for example, 5 meters per second of entrainment speed, 25 slip percent, that is 0.025 in slide to roll ratio, then you come to this curve 0.05 in friction, and you can do the same for the high viscosity, and you end up on the 0.045. So that means it's 10% lower friction with a high viscosity. That's maybe not expected for all of us. Just to finish here now, funny thing, or maybe something to think about. Friction coefficient is one thing, but it's the friction power we want to reduce. So even if the friction coefficient is as low or pretty low up here in the corner, we should remember that the friction power is the product of the friction force and the speeds. And since the increasing speed and increasing sliding speed makes the power very high up here, even if the friction coefficient is lower. So, and we can compute this friction power map instead, and that has the unit is megawatt per square meter. And you can think about this number. So we have something like 200 megawatts per square meter here, and the megawatt is pretty much. So we could actually see the 200 megawatt per square meter as putting a nuclear power station, a Swedish nuclear power station, all the power produced there at its maximum, putting that onto an area of 1 to say 5 square meters. Then you can imagine that we have a tremendous heating of the contact point. Of course, in the gearbox, the contact point is very much smaller than a square meter, but you still understand what kind of forces or some energies that is passing through there in the contact. Finally, a few words about some recent research. We have found that it's possible to reduce friction by adding coatings. That's that's not at all a new finding, of course, and coatings are used to reduce friction very often, for example, in mixed and boundary lubrication. But in this case, it's a full film lubrication case, and we found that even in that case, you can strongly reduce the friction, because the coating acts as a kind of thermal insulation. So the more indicate the nuclear power station in the contact, the heat produced there is normally, the majority of that heat is just conducted through the metal surfaces. So if you add a thin layer of an insulating material, which DLC coating is, for example, you will actually stop part of that flow, and more heat is remaining in the oil film, and that makes the oil warmer, and warmer oil also means softer oil, and this pressurized, almost solidified oil becomes softer, and the friction is reduced. And you can see that you have pretty significant decrease of friction coefficient if you add this coating. It's a new finding. You can read that in the tribology letters, for example. So that's all about gear efficiency for now, and so thank you very much.